Test 1, 2, 3, 4. Oh, there we go. So the audio coming through and my video stream is there's approximately 1 minute of a delay. And I will pause this music here and I'm trying to set up this camera, which is being extremely a major pain right now. And I actually forgot how I set this up. I wonder if I can... There's a way to twist this camera here. Somehow, somewhere. I know there's a way to twist this because I thought I did this before. Wait a minute, what's wrong with this? Wait a minute, there's something wrong here. Oh, there it goes, it's twisted there. So now I can do something like this. Is that what I was trying to do? So if I tape it there and then do this, I should be able to do something. Alright. This is the first time I have done this with this particular setup. I usually stream on Twitch. No, I don't know if I'm using that equipment or not. That is a generator. Supposedly we've got some voltage there and I need to probably tape those down. But I want to get this video camera set up so y'all can see some stuff here. And I'm totally not set up. I forced myself to do this, even though I'm not ready, because oh my god, that thing weighs a ton. Because that's what I have to do to get things started. So you gotta kind of force yourself to get into things. No, I don't know. That looks good. I've got another decade counter. Well, I can use this one. I just want to show off some of the equipment. I'm gonna start turning some stuff on. I had a plug down there which I took apart. Means I gotta plug some stuff in. Before I do that, let's see if I can tape this camera up here. That'll be interesting. I'm a little bit nervous, needless to say. But once we get going, we are going to delve into the world of what I call esoteric electronics. But before we do that, we're going to talk about all the stuff that's out there right now in the world regarding this stuff. Now before I do this, I'm going to turn this camera on. Over here somewhere, somehow. Let's see, where's the browser? I got a browser to set up. Uh-oh. What did I lose? I want the background in there. So, let's see, we'll bring this up here to fill that screen. What is that? My camera's not working for some reason. I may have to reinitialize everything. Let's see here. Settings, video. Video output is currently inactive. Please turn off any outputs to change videos. Yeah, I gotta restart the stream, I think. Huh. Yep. me just make a note there. Alright, let's try this again. That's good. Alright, so I'm gonna turn this music off. Wait till I have to reset something over there too, probably. Let's see here. Oh, it's working. Well, is it working? It was moving there a minute ago. So there's about a good minute delay, I guess, on the. So what I'm gonna do, this is a little bit difficult for me to do, but we're gonna make an attempt here. I'm gonna show you the various pieces of equipment that I have. Up here is a signal generator, and it produces sine waves, square waves, and such. I have another signal generator down there on the right. There's an attenuator sitting on top of a radio receiver right there. And then I have an oscilloscope over there. I've got a digital voltmeter. I have a couple of frequency counters up on the top of the bench over there. And I'm going to try and somehow put this over here. Things are going to look a little bit discombobulated. I also have a square wave generator down there. I got tons of stuff. This is not kids stuff. This is the real deal, Papa Schmeal. Now if I can just get everything. Right now the camera is going to be in a precarious position, and I'm trying to set that up here. Well, it won't be in a precarious position. It'll just be where it needs to be. Type of deal, you know what I mean? Yep. And I'll put that in there somehow. Actually, what I could do is I could play some of this music here. So while the music is... Oh, that actually looks pretty good. I wish I could get... Hey, wait, no. Let's see, is that... Somehow... Oh, there we go. Oh, there we go. I can try to even that out a little. So I can move things around a little bit. I'll have a scope set up over there. There. So now what I gotta do is I gotta turn on some equipment. I gotta bring a plug back over here. Yeah, we're gonna mess around with some with something. I don't know what, but we gotta get this party started somehow, because this is something that I've been wanting to do for a long time, and we're talking years. And I'm finally getting into doing this. Here's a little basic digital voltmeter that I've got here. I also have another meter up here, which I have issues with a lot of stuff, but just have to deal with it, I guess. So this is my other digital meter. It's a more advanced type of a meter. I always like to double check things. I probably won't be using that meter tonight. I mean, I might. I don't know. But I want to get some stuff turned on. And then what we'll do is I'm gonna mess around with this old circuit board. So you probably can't see it that well because that light is so bright. But there's a bunch of stuff on there. I've got some resistors, basically set up in a like a bridge type of a circuit. And there should be a well, actually, there's a bridge circuit here somewhere, and these other small resistors are used to fine-tune the bridge circuit. I got a bunch of wires connected in there that's not doing anything. I'm just realizing that now. Okay, so I have to analyze this circuit. What is this here? Oh, there's something, I think that's a thermistor. There's something really small and delicate in there that I didn't notice before. Alright, so some resistors there. This was attached to something. And we're going to check. That's a variable resistor. Well, anyway. So in this box here, if we can get a good picture, there's all kinds of electronic components I got in there. There's stuff that I have not soldered wires to. There's this guy right here, which you can't really see it very well, but it's a very sensitive potentiometer. I wish my light was set up a little bit better. I can just move that over. Let's see. It doesn't really show up that well. The light is so bright. But anyway, this is a, what is this? A 1K resistor. Brand new, never been soldered to. I have tons of these guys right here. These are also variable resistors. Now, like this one here, can't really see it that well, but I can probably put this into the circuit. And I have a ton of these guys. See if you can see a picture of this better. It's a metal variable resistor. And okay, everything's good over there. And I also have a ton of these guys. There's another one there. I don't know if these are all the same values. Oops, I lost that one. Alright. What is this value here? Probably have to have my magnifying glass to figure these things out, which I do have. Oh, that's 100 ohms. I wonder if I have. See, we're just kind of starting out with this stuff. That's 100 ohms. That's 100 ohms. What do we got here? That's a 20K variable. See, this I'm hoping well, that one I can't plug in because the pins are all messed up on it. This one looks pretty good. What do we got here? Ooh, that's 100K. I want some high-valued variable resistors. Oh, that's 100K. Maybe these are all 100Ks. Okay, this is a 20K. And that one's crooked. Let's see what else we got in here. I have tons of capacitors. I've got tons of diodes. Now, a lot of this stuff is mixed up, and I will be in the process of, that's a capacitor, of organizing some things. And you think, well, how can anybody use this equipment to do things that involve the speed of light and that sort of thing? Well, it all has to do with electrons. That's 100K. I was hoping for another 20K of that particular style. Oh, you know what? That uses a small adjuster, doesn't it? That's a 20K right there. I might be able to straighten them pins out and stick them in a breadboard. I got another large breadboard set that I'm going to bring over. And maybe I can just put this over here somewhere. Now, the first goal of my project is to build some power supplies. I'm not going to do that tonight because I'm just going to use a couple of batteries I got set up over here. There is some things that I would like to test. I would like to test preventing RF feedback from getting back into the power supply. And I got a few ideas on how to do that. You're supposed to use what's called an RFC, which is a radio frequency choke. And I did have some of them floating around somewhere, but they seems to have disappeared. We've got crystal oscillators that I would like to hook up and give them a try and see what they look like. See how they interfere with the power supply. How can I get rid of the interference from the power supply of that stuff? Because that's very important, is to get rid of interference. We got some things over there. I'm not going to use that. So like here's a bunch of chips. These have like integrated circuits. There's timers. There's some op amps in there. This is a ferrite core, which has a wire that's kind of wrapped in around through it, and we're going to use that to test RF choking capabilities into the power supplies. And I have what's called a mini engineer's notebook. You can't see it that well. It has various types of circuits. I have a lot of these. There's a transistor driver. So what I was actually looking for is, it might even be in this book, voltage to frequency and frequency to voltage converters. That's something that I have to build. And a lot of this stuff, there's SCR drivers, piezoelectric buzzers, LED drivers. These use basic discrete components. I tend to try to stay away from op amps if I can in the main circuitry. And we'll get into a big discussion about that at some point in life. There's a regulator. We could mess with that. That's the regulator circuit I was looking for, actually. We could do some messing with that at some point. So what I'm going to do is get my power strip, and I'm going to plug in that stuff that I unplugged earlier. I'm going to grab me some snackaroos. We're getting there with this project. It's going to happen, people. Chihuahua. Caramba. just hide some of this stuff here. Alright, let's see what we got here. So I'm going to disappear under the desk and try to hook this thing up here. This is a major pain in the Bruce Brutsky. To do. So I am underneath my desk trying to figure out how to plug this thing in. And I don't know, I don't think I can plug that in like that. Oh, it's a bit of a problem. You always have a problem. It's always a problem. It's not a problem, it's a challenge. That's a fucking challenge, is what it is. I don't fucking want to get that in. Okay, I got that plugged in. That's plugged in. That's right, we're plugging it all in. Time for the smoke test. We'll give it down. No, I don't know what the hell this white cable is. Must be the scope. Alright, we've got that. Let's see. Do I need anything else? Alright. Let the fun begin. That goes over there. I probably don't need this. I want my major breadboard. So I have a couple other breadboards kicking here. This one's got some stuff on it. I haven't looked at this shit for like years. So there's some stuff on that. You can't see it that well. And I'm gonna put that somewhere. Maybe up there. I've got this breadboard here, which is kind of newer. And I have another breadboard up here, which is a little bit more, it's got some more stuff on there. I've been messing around with things. You know, basically, I'm not going to use that one tonight. There is some things I would like to try. There's this box I box here. It's got transformers in it. It's like a old audio transformer. This round thing looks pretty cute. There's a transformer thing that I took apart. There's a coil in there. And it's got another part that goes onto it. Oh, you can't really see it that well. And there's a hole that goes right through the middle of it. And I have a laser set up here, which at some point what we're going to do is we're going to run the laser through a hole like this. Now there's also a larger core like this, which I have not, you can take this apart it seems, but I have not taken this apart to investigate the various coils in there. There's, what else have we got in here? There's some capacitors and stuff. There's a diode in here. I don't know what this diode's doing in here. What the value of that thing is here. This is, well, it says 1BS1. 1BS1 is what that is. That's a pretty hefty looking diode. We're not going to mess with that. But I have a bunch of these coils. And I wonder, you know, maybe what we could do is we could take the small one. Maybe we can investigate this small one here. Let's see. We're going to talk about something. I'm going to investigate this. I am monitoring the chat in case anybody's wanting to talk. There's nobody over there. So what I have to do is I've got to strip this wire. And it's going to be very difficult to do. I have a stripper. to talk about, like, with this setup with this coil thing. It's called resonance, and resonance is going to play an important factor in increasing the value of noise versus, or rather, increasing the value of a signal versus the noise that's around it. And what I want to do, I'm going to use this particular board, I think, because I can't see very good at all. I'm going to try to get that down inside the holes. Have it. No, it's not. I messed up on this other one. I didn't twist those wires around good enough. Maybe I can double up on that. Maybe not, I can't. Okay. So, things like coils and capacitors, they have what's called a, well, they have resistance, but they also have what's called a reactance value. And I'm not going to get into all the technical aspects. But that reactance value is based on frequency. And then you have what's called an impedance value, and I'm really having an issue with this. I don't know why I'm having such a problem. You have to, it does not want to go in either way. Just, so you have to have a lot of patience with stuff like this. My light is not, everything is not being conducive to happiness right now. I wonder if I can stick that in there. I can move those closer together. I can't get that in there. I might have to use, wait just a minute, I got an idea. Where did I do it? Right here. I have a pair of forceps pliers things here, so we're going to use that to put that in. That's much better. And I've got a way to force it. Very nice. Oh, spoke too soon. I think it's in there. It's going to hang. It's a deep end though. Oh, I found it. And I'll grab a couple wires here. I should have my test equipment running. I don't know if you can see what I'm doing. Let's see, where's... Yeah, you really can't see the board that well. The board needs to be over the middle, over towards the middle more. I suppose. You know, I've never done this sort of thing before, this streaming, so maybe that works a little better. Alright, so I'll grab me another wire here. And the first thing we'll do is we'll just check the resistance to make sure we have contact. And before I do any of that, we're going to start turning this stuff on here. Alright, so that generator's on. I'm going to turn on the scope. And I do have a meter here. I have a frequency counter. I may just turn those both on and kind of check them out. forgot I had to have my headset on. Everything is kind of in the way down here. This channel, I'm only going to use channel 1. And I'll move that down to the middle. There's that. I need to get my cables. So first what I'll do is we're going to check the resistance with this little red meter. And see what it is. It's probably something less than 200 ohms. And I'll check the meter first by shorting the leads. It's reading about 3 ohms for some reason. I don't know why. It's actually going over 200. 20K. That's interesting. No, I don't know what this thing is doing. It's acting weird. Let's go down here to the board. That's really acting strange. What's doing that? Let's go to the device itself here. That's reading 29 ohms. My leads are reading 1.8. The device is reading 28.2. So 28.2 ohms. Well, it's jumping all over the place. It could be because the battery's weak. I get 1.6 ohms lead resistance and 28.2. So we've got 28.2 minus 1.6. That's a total of 26.6 ohms. Alright, so we're gonna, well, we could say it's 26 ohms. Now, that's the resistance, that's not the inductance. So, I've got a variable capacitor over here, which is this guy. And it goes from microfarads down to nanofarads. It's got a bunch of stuff. And there's also capacitance within, it's missing a foot or something here, I guess, within the leads itself. And I don't particularly care too much. I'm not too worried about that, I don't think. I wish I had a couple of those. And I've got all of this wire here. Let's see, let's grab that pair right there. So resonance means that you will have an amplification of signal when the frequency is the correct frequency for the unit under test, which could be a whole system like a RLC circuit, a filter type of thing. And we might be able to use this, we might be able to make a filter such that we can do a noise test and run the noise through the filter, and then we can see a difference in the amplitude of the signal. That stupid stuff does not want to come apart because it's all sticky. That's what it's all about. Now, I'm going to interject, and we're going to go on the online and look at some stuff once we get a little something going here. We're going to talk about this ghost box thing. The ghost box uses what's called like noise in order to get ghost talk and mixing of noise signals and radios sweeping the radio channels and all that kind of stuff. Well, I know all about the ghost box, and you know, we could mess around with something like that. However, take my advice and don't use it. It's a waste of time. Trust me, you're just wasting your time. I don't know why in hell that's not coming out of there, but it's gotta come out. Oh, it's crooked or something. I got a really thick wire in there. What the hell? Oh, pull it out this way, I guess. There we go. Now, one of the things that you always have to be aware of is what is called interference. There's all kinds of radio signals and interference that exist in the atmosphere and everything else, and wires and everything else pick that stuff up. So we have to take all of that stuff into account when we build our circuits. And this includes using, well, what I've discovered and what I believe is that what we have to do is we have to use discrete components. And if we use discrete components, we can eliminate much of the interference that we get in the outside world. I think I might have to, if I can get this wire in there. There we go. Sort of, I think. Now, this is our variable decade capacitance decade box here. And we got some wires hooked up. And I will put this in a couple slots here. And you're probably asking yourself, like, how could you do anything as sophisticated as faster than like technology using equipment like this? It's based on the idea of just using electrons, and electrons happen to travel at the speed of light. Or so they say. There is a 0 setting on this. I'm just going to leave it right there for a minute. I'm not picking up any resistance at all on this capacitor box. Let me get my other meter down here. This meter does measure capacitance and such. And yes, I do have enormously long leads. We're working under what I consider worst case conditions. So we're reading about 6 nanofarads, and that's pretty much what we've got here. That's just 0.005 microfarads. So what I'll do is I'll set this all the way down to 0. I don't know if that shorts it out. And that's 0.5 nanofarads at 0. So I don't know why it's reading that. That's 1.5. That's 0.5. No, I don't have a way to measure inductance. I'm assuming that that coil will probably resonate at some audio frequency, and we can probably pick a capacitance that will match, will give us an impedance that will get us a good reading. Yeah, something like that. Now I'm looking for connectors. A connector here, which doesn't have the right other connector, does it? Well, let me have to go into my box. The way things are going, I'm not going to get to power supplies. I mean, there's so much. Well, I mean, it's not like there's a lot of stuff to do. But there is a fair amount of things that need to be done. Alright, so here's a piece of equipment here I could plug into. Let's see, what do we got here? See, I don't know if that's a mixer. So if I use this, I thought somewhere I had another connector in here. I got so much stuff that I just don't know where everything is. I don't think there's anything here I can use. I seem to be missing something. I don't know what. Oh, maybe it's this. Can I use this? This might be the only thing I have. So I can go into there. I'm missing a male-to-male. That's what I'm missing. I went to the electronics free market. I'm supposed to have all this stuff. And I don't. Alright. So I can use this to go to. Well, that's the male. I've got the female. That goes from there. I have to go from there to something. I love this job, I'm telling you. It's like I got probably like one connector that does what I need, and I don't know exactly where it is. I'll get things sorted out someday. What the hell? There's something, but that's not what. This is ridiculous. How did I come off of that? So I could run this with a T, and I could go. Oh wait, just a second. I know what I can do. I can go from there to there off a T. I think? No. I'm still missing something. Huh. This is distressing, to say the least. Oh, God. What am I missing? That probably shouldn't be down there. Huh. I know a banana to a male is a rare connector. I should be able to go from this. I can go from there to the meter. Wait, okay, wait just a second now. We'll get this figured out somehow. Okay, see that one's got the holes in it. That's what I need. Okay, so if I hook this up to that meter there, and then we go like this. Make sure that this is the correct side here. Then I can go from there to B and C. I'll use this long one. So I got here, I need a female. That's well, that's an interesting piece of equipment. Looking through this box of stuff here. There's an attenuator. I don't really need that. What's that? No, I don't need that. Huh. Seriously, these are all male connectors? What the hell? What am I missing? See, I want to go from there to there. But I need another... What's this? That's gonna work. Well, I could use this attenuator. I never had to use this before, though. It would be kind of interesting. This is... I don't know, that's not for audio. I think it's an RF attenuator. All I've got is this weird male to female thing. Strange. I'm missing a connector. Oh, what am I gonna do? Ridiculous. Totally ridiculous. If I get to B and C, gets me my... Wait, that gets me... I'm still gonna have to switch. Oh, something's just really not right. Oh, you know what? I know where there's a cable. I know where there's a cable. I'll just put this out there for now. I think there's another cable kicking around here. Where did I see it? I'm sort of not prepared, as you can tell. It's just par for the course, I guess. No, I don't know what that cable might be up here. There's a scope probe, which I could actually probably use. I don't know what's up in here. Okay, here's something there, which may or may not work. a scope probe, which may or may not work. Let's get something on there, an RCA connector. I don't know what that scope probe for tonight. I know I've got another connector with B and C's on the end of it. I don't know where it went. This one's broke. That's not going to do me any good. I may have to look for that cable. This is just not good. Okay, well, how am I gonna, what about a mail to mail? Don't I have a mail to mail? I'm just missing some stuff. I don't know why. I had bought a bunch of connectors. I thought I threw them in here. Shit. I don't know where the heck it is. There's the mail to mail. It's not in here. Nope. Not there. I wonder what's in that box. Let's see if I can just pop that guy right there. There's no connectors in that. I don't think there's any in here either. I got a cable. I'm gonna have to get up and go look for it. I know I've seen that cable around. Now there's some other stuff in here. There's an audio transformer. Probably won't use that. It's a ferrite core and a magnet. I gotta get up and look for this cable. Alright, so what we're going to do is going to grab this cable here, hook this up to the generator, which is set to sine wave in 1 kilohertz or something, and I will connect this directly up to the scope for now so that we know what we're getting here. I've got this set at 0.1 volts, 0.2. Turn the intensity up. I don't think you can see that in the... Oh, you can actually see that sine wave. That's pretty cool. Alright. There's triggering. right there. So what do we got? Yeah, it's about 0.24, like 24681. It's about 1 volt peak to peak. I don't need that much amplitude. So we'll crank this down. We could probably even use the low. I don't think the low works for it. Oh yeah, it does actually. So that's a couple of 100 millivolts peak to peak. So that's pretty good. I mean, we can go up to, yeah, we can move it up. So I'll use that, and what I will do is connect this to, so we've got that capacitor. I don't know how to do this because I don't know. I know the resistance is 28 ohms on that coil. Let's say that's a coil, and I run let's see what we could do. Why don't we grab, I know that one of those is 100K, but do I have a tool? I do. It decided to disappear on me, but I do have a tool there. I wish I had one of the other resistors. Oh, there was 120K in this pile. That's a 20. It's messed up. That's 100. Oh, actually, well, that's 100 ohms. What else? Wait a minute. That's messed up. That's messed up. The ones that are messed up are probably, and I could use 100K. Probably any one of them too. If I can get that to go in there somehow. Okay, that's, I can't see what I'm doing, but that's par for the course. I'll grab some wire here. So there's one there. And there's another one. And that one is right here. Shove that back in there. And then I will grab this guy. I'll hook this up to this variable resistor here. And change that to resistance. And we're reading, it says reading 8K. Let's see if we can adjust this little guy here. That's stuck in there. Where did I see that screwdriver? There we go, gotta move it there. Okay, that's good. So we could probably set it to 10K. Somewhere in there. So that's 10K. And I will put that in series with this other coil, with this coil over here. What we're going to do is we're going to see if we can find out what the resonant frequency is of the coil. Alright, so we're going to go from there to there. We'll take this one out. Go from there to the capacitor. here, over to here, and we're going to take this adapter thing that's just buried down in here, and it's not quite going to reach, so I'll move this over here. Now, how did I do this? So, if I use this guy, let's see, that goes, where's my T? I need some T. I didn't seem to have taken one out. I don't know why. I'll grab me a T here somewhere. I know y'all, most people think, well, this guy's just messing around with electronics. Yep, that's what I'm doing. Let's see, I still cannot, I need that male-to-male connector. That's giving me a problem. Oh, well, I could. I need to hook it up to the scope. If I go from there to there, I still need male to male, don't I? To hook up to that scope. Oh, I know what I can use. Alright, I've got to look for something. I think there's another, I noticed another RCA in here. Where did I see that? Bada bing, bada bing, bada boom. There it is, right there. I found it. Okay, I've got that. And I just need an RCA connector to connect those two things up, don't I? Alright, so what I have is an RCA connector which supposedly does not work. And I will grab the red one here. I'll hook this up to the scope. Just run that down there. Where's the other section here? This goes there. Now this goes to the scope. And I'm going to connect this to somehow. Wait, what's wrong with this? I got this backwards. I think. That's the shield, and that's that part there. So it's going to be like this. That goes in there. And that should be connected to the scope. I'm not sure what's going on there. I'm picking up a DC level for some reason. Let's disconnect to this. And I need some energy food. I am watching the stream, sort of. I don't know quite what's going on. It's acting like I have a short now. There shouldn't be a... Oh, I know why. Wait a minute. I know why. Let me disconnect this. There should be... I should be reading a resistance. Well, something's majorly wrong now. What's going... Oh. What's going on? There we go. I've got a... Oh, you know what? It's this connector. I wonder if I can tape that. I want to tape this and see if that helps. I seem to have... I may have a loose connection. That was just saying that it was open. We'll just mess with this here a little. Alright, now I've got a good connection there. So we'll go back to over here. And I should have, well, if I measure off of this wire, I should have, it's, well, it's a little bit messed up here. Should be reading about, yeah, it's reading about 10K, okay? I'll go No, it says it's open because DC will not go through a capacitance. That's why that's reading open. So now we're going to change this to AC voltage. And I will plug that into there. Now I've got 2 voltage meters connected. And then this goes into, I don't need this, I just need this. And this goes into there. Okay, so now that added, that changed, well, yeah, that's the generator. Alright, so I've got 137.5 millivolts on this meter, and I've got 0.137 on the other meter. So I'm just basically testing out my meters, because I haven't used them for a while. And so that all looks good. Now, if I crank the amplitude, the amplitude does show up over there, but it's not showing up on the scope. That's where we need the T. Oh, you've got to be kidding me today. There we go. Alright, now see, that reading's different now. So if I disconnect the scope, it's still reading the same amount. I'm wondering why the voltage is different. Alright, so it is the same. It's reading 0.273. So I think we're good. We'll hook this up here. And we'll watch when we connect this up to make sure that the voltage doesn't go down on the scope, which it doesn't change that much. And we can crank this up a notch. Alright, so now what we do is we find out if there's resonance, if we can find a resonance peak in that coil. And in order to do that, we simply change out the frequency. And now if I disconnect, if I take the coil out of the loop altogether, we could probably do that with another wire instead of just pulling that out, maybe. Let's see here. I need I need more cables. That's what I need. I'll just cut this wire here. I wanted to do this shit like fucking 10 years ago. You know, 10 years ago. I've been waiting to do this. That's a long time. My wife passed away. I had a girlfriend who didn't give a fuck about me or anything that I did. I never should have let that shit interfere with my life. I wasted a whole fucking year of my life because of her. Thinking that things were going to be good, and you know, when a person doesn't believe in you and doesn't even give you the time of day for your own projects, there's something wrong with that. And I don't think that's right. I mean, we're just human beings, you know. We were brought up a certain way, and we're all different. So what I'm going to do is I'm going to short this coil out here and see if we get a change. Okay, that's shorting out the coil, and obviously you can see there's no change in the resistance, which is more or less to be expected. Let's crank it up. Let's see, we're sitting at 1K. Let's crank it up to 10K here. That's 10K. And see if we get a change in value here. Wait a minute. No, there's no change in value. That means there's no resonance yet. Of course, I'm using that capacitor, which is a very, you know, maybe we've got to put in a different value for capacitance. I wonder if we could use, let's see, where's that box? I don't think there's a capacitor in there. I've got capacitors up the yin yang. There's this one here. There's that one. Oh, there's a nice looking one right there. It's an electrolytic. That I think is a capacitor. There's one there. There's a bigger one. I don't think the big one's going to do any good. Let's try this capacitor here. I don't think this other, well, we can put capacitors in parallel and they will add to the capacitance. If you put resistances in parallel, the resistance goes down. If you put capacitors in parallel, the capacitance goes up. So that obviously didn't do anything. Let's put in this guy here. And I don't think it makes any difference which way we put it in. Just have to make sure we get the right hole here. No, there's a dip, but that's just because of the generator. So I'm not having any luck here finding the resonant frequency at this coil at all. Why don't we pull out this altogether? I'll just put this in here. Wait, let's see. We're looking at the whole circuit, aren't we? I may have to dispense with this coil for tonight. Yeah, it's not. I don't know why that's jumping. I got a loose connection or something. That capacitor's not doing anything either. Let's see if this little guy does anything. I love playing with their shit. Nope. Well, interesting. You'd think that I'd get a resonance somewhere. I'm using 10K You know, if I go through the formula and make a filter, that's one thing. I gotta have a bite of this and think a minute. So the frequency, the resonant frequency is going to be 1 over 2 pi times the square root of LC. In an RL circuit, the Q is a ratio of the energy stored to the energy dissipated per cycle. Q value of a tuned circuit is related to the bandwidth, and they are inversely proportional. So for a narrow bandwidth, we have a large value of Q. If Q is large, inductance has to be large. In order for Q to be large, R has to be small. Well, it's 28 ohms. But it's probably, and I don't even know if that, well, I got a 28 ohm resistance. Strange. Bandwidth and half power points in a resonant circuit, etc., etc. So you would think I could probably just hook that generator up to that coil, because it has resistance. I don't have something that measures inductance. It only measures capacitance. I'm just checking my stream over here. Anyway, well, let's try that. Let's grab the generator. We'll crank the level down because I don't want to make sure that it's messes up anything too much here. Let's go right to the coil. Oh my god, I can't even get that wire out of there. So if I go from there to here, well, the coil, that's 28. It's 50 ohms into 28 ohms. So there's a load there, but it's not. I'm using a low impedance output on the generator. Now if I go here, that shorts it out, okay? Well, it's not shorting out the generator. Wait a minute. You know what I want to do? I want to disconnect the generator again. And I want to see if I can measure. It says 26 ohms. Okay. Now I should be reading a value on my Why is that different? That's on a 20 millivolt scale. And I'm reading, well, it's 50 millivolts. It's just reading small. I think there's a level adjust on that meter. It doesn't read 50 millivolts. This one's reading, well, it says 0 millivolts. Wonder why it's not reading it. Where is... This cable goes up to there. So that's reading right across the coil. Let me just crank this up a little. Well, you know what? The coil is not having any effect. It's not... I can't get a resonant frequency. Anyway, I think we're going to have to dispense with that. Why don't we take a look at this circuit that I've got over here, and maybe I can explain what that is. I'm a little bit discouraged by that coil. I wonder, you know, I've got some other coils in here. I wonder, let me take a look at this one, just out of curiosity. Let's see, these are not cut, are they? Okay, this one's cut. Let's take a look and see what we've got here. I'll disconnect this. And we'll measure. I don't know if I disconnect that. I shouldn't have to. Well, those wires might not be in the correct configuration. Now that one's reading 7 ohms. Let's hook this baby up here and see what happens. 100 millivolts. No, that's just going down in level. I don't know if that's due to that coil. There is a drop off there, which is actually rather considerable at the low frequencies. Let's put this across. Oh, I took that wire out, didn't I? I'm going to put it across this resistor. This guy going everywhere. Oh, that's interesting. That value is going up. Okay, so we've got something going here now. Let me just see, that value is going up as the frequency goes down. So if I back to, let's go back to this guy. Now see, this one here is not changing. Well, it does go, it's actually going up at the lower frequencies. If I go to this one, oh, that's a major drop right there. What the heck? Oh, it really, there's actually a dip in there on this one. So, interesting. So what we need to do is accentuate that dip if we can. See, it actually goes up. Oh yeah, there's a dip there. Sweet. We gotta find out what frequency that is. Let's see, let's crank this up here. I may have to go to the high level. Okay, so there's a dip there. Now we can find out exactly what frequency that is. We can see the level. Like, I can monitor the level on this, and we've got another connector up there. So we're reading 0.73, 0.72, or 73 millivolts. So that's 6460. Right now, that's, I don't know why it's doing that, because the peak to peak level is going up, and that's probably the frequency response of the meter at low frequencies. Now I don't know if the meter is actually causing a problem with that, so let's take this out. Let's check this again. Okay, there's still a dip there. Now I want to look on my meter here. This is a high impedance meter. They both should be high impedance, but see, that value is going down. It's staying the same while it's going down there. It's not going up at the low frequencies. And that's reading, that's 1 kilohertz. Oh wow, so that's, this one's got a resonant, a dip at 1 kilohertz. So what that means, instead of, it means it has a dip. So instead of being resonant at that frequency, it's acting like a cutoff. It's cutting off at about 1 kilohertz. Now, if I put, I don't know what that capacitor would do. I'd have to look at that formula. So if we're using 1 kilohertz, and it's a band reject, well, the bandwidth, I don't know what the bandwidth is, but in order to get resonance, this is not what I want, though. I don't know why it's dipping at that frequency. It's like I'm being counterintuitive as to what's happening. But anyway, it's sort of an idea, I guess. So if I use this formula, I don't know what C is. If I use 1 kilohertz, I don't know what the inductance is. Inductance at 1 kilohertz. Alright. Resonant frequency is reached when the capacitive and inductive resonances are tuned circuit are equal. A series LC circuit has 0 reactance at the resonant frequency. That means it's a short. A parallel LC circuit has infinite reactance at the resonant frequency. So that means it's an open. Now, if we have, so what I could do is I can either connect a capacitor in parallel or in series with this. Now, because I have a dip instead of a peak, I think I want to have either one or the other. So in other words, all right, so if the frequency is going, wait just a second. So either way, if the frequency goes up or down, the inductance and the inductive reactance are proportional. The capacitance and capacitive reactance are inversely proportional. So if we just deal with the inductance for right now, that means, let's see, the inductive reactance equals 2 pi times FLC, I think, or FL, or I believe, something like that. I don't know exactly what that formula is. Let me just take a peeky here. Inductance, conductance, reactance. Okay. So the inductive reactance is 2 pi times L. So if the frequency goes up, if that's connected in a series, well, yeah, if it's connected across a load, either way it goes up. So if the frequency goes down, the inductive reactance is going to go, down. So that means on either side of that frequency, the inductive reactance goes down. Inductive reactance is similar to a resistance, okay? So if I want to maximize that frequency, do I put the capacitor in parallel or do I put it in series? That was the question. Normally I would know that answer. Susceptance is the reciprocal of reactance. Conductance is the reciprocal of resistance. Then you've got impedance, which is the total reactance of the circuit, which is resistance plus reactance. And impedance is related to okay, so that's a square root. Here it's RXL over, that's a tangent formula. I want to look at this Q here, this resonance. Alright, so if the frequency goes up, no, the inductance is going to be the same, but it goes up on either side. So we want to counteract the value of the frequency so that when the frequency goes down or up, the capacitive reactance we want to go down or up. They're already inversely proportional. I would think you'd put it in series. If I put it in series, then all I'm going to do is just I'm going to negate this. What the heck I'm trying to do here? Oh, the pain, Dr. Smith. Universal resonance curve for constant Q. Blah, X equals Q times the difference frequencies between the frequency and the resonant frequency over the resonant frequency. So where F is 1 over 2 pi LC at 1 kilohertz. Oh, wait a minute. Okay. Here we go. So I've got 1 kilohertz. Alright, here we go. I think I can, well, we can come up with something here. Yeah, the old handy dandy calculator. Alright, so if we take the resonant frequency, which in this case happens to be 1 kilohertz, times 2 times 3.14, equals, we come up with that number. 6,280 equals 1 over the square root of LC. Now, if we take the inverse of that number, 1 divided by 6,280, we get a number where the inductance and the capacitance equals a certain number. And if the inductive reactance goes up in both cases, in order to negate that, the capacitive reactance has to go down. But that would really make any sense. It just doesn't make any sense. It's been so long since I messed with this stuff, I'm telling you. Because I don't know what the inductance is. Let's say if I use a capacitor, this is 1.5 times 10 to the minus 4. Let's see, 16 times 10 to the minus 3. What is that, 16? That's millifarads. Wait, 159 microfarads? 160 microfarads? 160 microfarads, that's a big capacitor. That's a huge, well, that's a big capacitor. Wait, so if I use 160 microfarads, then that tells me my inductance, that relates to inductance of 1 Henry. So if I divide it by 1,000 instead of 160 microfarads, if I use 0.16 microfarads. I had that on that little machine over there. I think I had that. Let's take this little coil here. So we're using this coil thing here. We're gonna mess with these wires. I wanted to build just a simple resonant circuit, you know. I don't think we're gonna get there. I picked up some coils at the little ham fest, but yeah, what are you gonna do, you know? Thing's really hard to stick in the board. See, like, well, people would come on and say, well, what are you trying to prove? I'm not trying to prove anything. I'm trying to discover something. See, these need to be soldered and wired up so that they go down to the holes easier. I can't get that in there. That's not, oh, maybe I did get it in. I don't know. Let's see here. Where did my little cable thingy go? I lost it. Let's see. I don't know what this thing is. Well, we're looking for 0.16 microfarads here. Uh-oh. Uh-oh. What, is anything connected to that? Well, the scope, oh. Let's take that off. So that's 1 nanofarad. That's like 0.001 microfarads. I think. Well, I don't know what this thing is reading. Yeah, something's not right because the scope is hooked up. Yeah, I don't know. I don't know what's going on over there. Oh, it's a sad day for... It's a sad day for this job, I'm telling you. What do we got here? Alright, here's 0.47 microfarads. If I had two of those in series, I could come up with 0.22 microfarads. And we're looking for 0.16. I mean, it's not really close, but why don't we just take this? We'll put this in series here. Just for kicks. Let's see if we can get a sharper dip. Alright, so that goes there. I'm going to need another wire here. Things doesn't want to cooperate with me. Alright. Let's hook all this mumbo jumbo back up here. Alright, so we've got a capacitor in series with this coil. That should be there, probably. Well, it's not reading anything. The meters is not reading the lower values. Okay, see now, wait just a second. Oh. See, that number's going up. That value is going up now, it's increasing at the low values. Okay. So if I... See, that's just going up right there. It's going down at the... It's going up at the low values. So it's acting like a low-pass filter right now. It's cutting off. Now if I take the capacitor out, now the values oh, there's a dip there again. Okay, well actually there's not, well there is, you know what, it actually kind of stays constant. Well, it does go up at 200 kilohertz. It goes up, it stays constant for quite a ways, and then it goes up at 50K. Now if I add the capacitor back in, there's more of a dip at 50K. So there's a stronger dip there at 50K when that's in series. I've put it back out. So in general, it looks to me like the level goes down as the frequency goes down. So when I put this capacitor in series, it goes down, but then it goes back up at the lower frequency. So there's a peak So it bottoms out at right at 50K. Now, if I take that same capacitor and put it in parallel, there's a dip and there's more of a cutoff. I'm using the same output level, and the dip is around 200K. That's 10K. And that's 500K. Yeah, that slide goes back up to. What is it doing? Let's see. That's 100. 2 times 10 is 20. So it's 200, 300K. So like from 200K to 500K, it's flat. There's a dip there. In a way, that's sort of interesting. In a way, that's rather interesting. I wonder if we could take that capacitor and put it over that other coil. Alright, so let me look at this again. So from 200 to 500, the output level that I'm getting is about 40 millivolts peak to peak. If we go back and do this, that level at that frequency, it just constantly goes up. Oh, there's actually a peak there. There's actually a peak at about 2 megahertz or close to it. Ooh, that's interesting. Is that 1 megs? There's actually a peak at 10 kilohertz, 100 kilohertz. 10 times 10 is 100. There's actually a peak almost at 1 megahertz. It's right around 1.3 megahertz. There's a peak there. And then it goes down. And I don't think that's a product of the generator. And it goes down quite a lot. And it does go back up. And that's at 50K. So it's acting like a band reject. Meaning instead of like a resonance, it's resonating, but it's rejecting the frequency that I actually wanted to, I was hoping. It's rejecting outside frequencies. So I'm just wondering, how can I use this coil and laser light in order, what frequencies how can I set this coil up so that I can monitor certain frequencies that will get either amplified or rejected, or if it rejects everything else, it acts as a filter. And that filter, even though it's not the greatest, it's better than nothing type of thing. Because it will add to your signal gain by getting rid of that noise. So that level there is a lot higher. Well, it's about 150 millivolts. And then there's another dip up there. That's a peak. I don't like that. I don't want to use that though. 50K. It's possible. It's possible to use this. If I can find another capacitor in there. If we could drop that level down. So if we want the resonant, if we want the band, well, that's rejecting 50K though. That ain't what I want. I want to improve. I want that resonant frequency to go up. I don't want it to go down. So there's these equations in here. I'm looking at a particular book here. It's got like everything in it. Where did I see that? I mean, I know I can make my own filter, but the point is coming up with. All right, it has to do with what's called a Sparacom device, where they're using two different frequencies, like audio and CB frequencies or something. And what I want to do is run a laser light through this coil and use the coil as a measuring device. But I have to know what frequencies this thing operates at in order to measure anything. Alright, so for the resonant frequency to go up, the inductive reactance has to go down, and the capacitive reactance has to go up. If capacitive reactance goes up, capacitance goes down. It's notching out. That's what it's doing. Why is it doing that? It shouldn't do that. It's acting in both cases, whether that capacitor is in series or in parallel. I wonder if it's because of the effect of the ferrite core, and that's why it's acting the opposite. I don't know. I wish I knew. Alright, you know what I'm gonna do? Let's try. Let me look at some shit here. Let me look at some shit here, right? Yep, right. Yep, right. Oh God, I can't put that up there. This shit's too heavy. I got too much stuff. I don't know where to put it all. There's some capacitors in here. Maybe we can find something that does something peculiar. Let's take this guy here. Actually, let's put this guy in. You see, that didn't do much, but okay, see that? Well, that's actually peeking out. But I don't know if that's a product of the coil. Let's see. If I leave that open, yeah, see, the generator is going down at that level, but it's staying. The generator is fairly flat until it reaches about 2 megs. Then the level goes down. So that's not a product of that. So it's definitely going down. It's acting as a high-pass filter. Acting as a high-pass filter, so that means, but that's in series. A high-pass filter is usually in parallel. Like if you make a bridge, you got a capacitor, then a resistor, then another capacitor, and they're both, the capacitors are in parallel, the resistors in series. No, wait just a minute, I take that back. It's high pass in series because the capacitor looks like an H, and that's what that is. I want a high pass filter. No, I want a low pass filter. Let's put this baby in let's see, maybe I can grab another wire. Let me grab another wire. Some wire. I have to make another one, don't I? Use this one. I'm gonna put this capacitor in series, and supposedly that makes it a high pass. Wait, capacitor in series makes it a high pass. A low pass. Yeah, I wanted to make a low pass filter. That's what I wanted to do from this particular stuff. Oh, something's really whacked out in here. Is it shorted? I don't think so. That's the green, that's the blue. Wow, that really did something. They really cut the level down quite a lot. It's acting as a high pass filter. It just dropped the level down quite a lot. Not good. Not good. What time is it? I don't even know what time it is. And the reason why I asked is because I wanted to look at some stuff. Alright, what else we got here? There's a 50, there's a 330 microvolt. I don't want to use them. There's this guy. Let's try this guy out here. This also cuts the level down. So if we take this wire out, now we've got our dip. Well, that's a very sharp cutoff at a low frequency. That's at like, what is that anyway? Oh, that's a very sharp cutoff. Wait a minute, is that 1 kilohertz? Wow. No, there's 2 kilohertz, which is pretty low. It's 1 kilohertz. It's actually going back up. Two kilohertz, 1 kilohertz. See, that's 100 millivolts peak to peak. And then it goes down to about 10. So that's a sharp cutoff. Let's see, that's 100 millivolts at 200 hertz. And that goes up to there. I must be missing something because I haven't messed around with electronics for so long. Huh. Oh God, what am I thinking? Alright, I'm going to look something up on the internet here. And see, what am I doing wrong? So, let's see here. So, let me just type something in here. is so complicated. Low pass, high pass, amplification. It's a notch filter. That's a notch filter. By combining basic RC low pass and RC high pass, we can do a simple band pass filter called a band stop filter that can block or at least severely attenuate a band of frequencies within these two cutoff points. So a notch filter, it makes that frequency come out clearer because it's eliminating some stuff. But I thought that's what the bandpass filter did. Strange. Band stop response. Band stop filter. 200 low pass filter section. High pass filter, they're using a resistor and capacitor. This is high pass filter section. We're looking at, actually, we can look at browser. So if we look at this circuit here, it's a basic op-amp circuit. You've got a signal coming in, and you've got this stuff going on here. Excuse me. It shows you your relative frequencies, 800 hertz and 600 hertz. I mean, that's a really narrow range. So if I used 10K resistors, what they got, an 8K and a 2K. At the resonant frequency for the low cutoff. Okay, so what we could do is, that's 8K, isn't it? See, I just don't want to use an op-amp. I mean, I would just use, like if it was me, I want totally passive, so. And then you've got to match the impedance, because you have input impedance and output impedance. Whereas if you use an op-amp circuit like this, you don't have to worry about it. actually, the way they've got this connected here, it doesn't, something don't look right. Because you could have a frequency feeding back from this op amp into this one, creating noise and crap. There's a twin T. See here, the input impedance and output impedance are identical. The upper T-pad configuration, which is 2R and 2C, configure the low pass section, and the lower T-pad capacitors are just from the high pass section, which is H. See, these capacitors are the same. They look like the letter H, so they're in. There's a capacitor on the input and a capacitor on the output. They look like H. That's the high pass section. The frequency at which this basic twin notch filter offers maximum attenuation is called a notch frequency, and is given thus. That's a formula I never learned. Being a passive, one of the disadvantages is that the maximum value of the output below the notch frequency is generally less than the maximum value of the output above the notch frequency, due in part to the two series resistors. In other words, you get a lower output than you get on the input, even though you still have the filtering, which just really isn't a big deal. Having great reactance of two series, as well as uneven gains on either side of the notch frequency. Another disadvantage is that a fixed value, it has a fixed Q value of 0.25 in the order of minus 12 dB, which is not so bad. This is because at the notch frequency, the reactance of the two series capacitors equal the resistances of the two series resistors, resulting in currents flowing in each branch being out of phase by 180 degrees. We can improve this by using positive feedback. Now you've got a fully adjustable Q. Band stop filter example number 2. Well, I don't see, I have to use discrete circuits. I wonder if we can build this. Our notch, we know what the notch frequency is. We could pick a value. We could figure this out, actually, I think. Didn't they do this earlier? They're using 800 hertz, 200 hertz, and 800 hertz. And what we got is, like, with this capacitor connected, I can tell you what the upper cutoff is going to be. That's pretty low right there. So we need like a dB of difference, and I don't know if I can crank this up. Let's see here. I don't know why this isn't reading. I had to reset it maybe. That's 55 millivolts. 46. Okay, there's 50 millivolts. Now if I go, I can change that to dBm. There's some weird stuff happening with the frequency. Oh, look at that. You can't see that, but there's some distortion in there. There's some distortion writing that But I mean, in general, it's okay. We can live with that distortion. That's still intelligible, I think. That's 63 millivolts. So that's reading 55 millivolts. Let me see what the dBm is here. So we've got minus 23 dBm. So the power point, and that's at 2 kilohertz. Oh, the dBms are, well, yeah, it's going up. So alright, so the power points are going to be at minus 20 on each side. And I don't know what frequency that is, but we can, I don't know if this measures frequency. It probably does. That's like 1 kilohertz. I mean, it's close enough to 1 kilohertz. We don't have to be like, I mean, a little bit more, you know. Alright, so let's go on the other end. Let's see about where that is. That's about 3 kilohertz. So we've got 1 kilohertz for the low pass and 3 kilohertz for the high pass. And what I will do is I'm going to actually figure this out because I want to see what I want to see what the change in distortion is and see whether or not we can use that information on the information highway. Yeah. I'll be right back, Jack. No need to be caught, right? Set free. Now, since I stop the stream and I'm going to restart it.